All right, welcome back to GLS4OM. This is our last lesson in Unit 7, Techniques of Integration. Today we're going to be looking at numerical integration and Simpson's rule, Taylor polynomials. All right, joke of the day. How do you make 7 even? Give you a few seconds to think about that. And then thinking in a non-mathematical sense, but in a maybe English language sense, simply remove the S. Ba-dum-tsh. Okay, moving forward. Want to make sure I've got my pencil ready to go. That's looking good. All right. I mentioned earlier that you can take the derivative of every function, but you cannot take or find an antiderivative or integrate every function. So there are functions that exist that do not have explicit antiderivatives. You can't come up with a formula for it. The square root of 1 minus x to the fourth, the ln of x, e to the negative x squared, and 1 over ln of x. None of these have explicit antiderivative formulas using what we would call elementary functions. So we'll see today, what are we going to do? How are we going to handle these? First thing we could do is approximate the area using a definite integral, like we did with Riemann sums. So I'm just going to take you forward and just remind you. When we use the trapezoid formula, we saw that all of the sides, other than the leftmost and rightmost one, appear twice. They appear in two trapezoids, this side and these two. This side appears in this one and this one. So we went over that already. So what we have is y1 repeats in 2, y2 will repeat in 2, y0 appears once, yn minus 1 will also appear in this one over here, yn only once. So in the end we summarized it like this. The formula for the area of a trapezoid is 1/2 the height. The height of all of these are delta x, and then when you add the a's and b's, what you will get is this formula. So the left and the right ends appear once and everything else appears twice. That's a reminder of the trapezoid rule. The midpoint rule was the other one we looked at. So here's our rectangle. We're going to use this midpoint right here. I'm going to call that C1. The midpoint of this one C2. The midpoint of that one C3. And in our heights, delta x is going to be the width. And let's call the height of this rectangle would be f at C1, f at C2, and so on. So each one of these heights has to be multiplied by the width, and that gave us that formula. So what we're going to see now in math is that Simpson's rule is using a weighted average of the trapezoid, which is why I reviewed that one, and a weighted average of the rectangle based on the midpoint. Since the midpoint rule is twice as accurate, it's given twice the weight. So in our weights, we'll do a 1/3 trapezoid, 2/3 midpoint. And we are dividing into n subintervals. And for the trapezoid rule, we're using the even endpoints, right? So this height should appear once, this one twice, 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 twice. The last one will appear only once. And in our midpoints, the midpoint of these rectangles is going to be x1, x3, x5, and so on, which means the height of the rectangle is going to be y1, y3, y5, and so on. So we come to our formula here. We're going to take 1/3 the trapezoid and 2/3 of the rectangles based on the midpoint. So 1/3, the formula for the area of a trapezoid is 1/2. Now, where is this coming from? So the width of one rectangle is delta x, but we are now 2 wide. So view this as 2 delta x. Same over here. The width of this is going to be 2 delta x. So the width is 2 delta x, and notice the left end and the right end point appeared once, and the other ones appear twice. And remember, those were occurring on even markings. Just taking you back over here, those were occurring on even markings, y2, y4, and so on. Coming over here, we're going to take 2/3 the weight of. The width of all of our rectangles, just mentioned, was 2 delta x from over there. And then the heights were based on the midpoints, and I said the midpoints would occur at the odd markings. So that's going to give you y1, y3, y5, all the way out to yn minus 1. 2 times 2 is 4. multiplying all of the pieces in here by 4, leaving the 1/3 out in front. 1/2 times 2 is just 1, so I'm going to leave that with delta x. So I've got a third delta x, a third delta x in front of each of these. That allows me to factor out the third delta x, and then watch what happens. We get y0 and yn on the ends appearing once, and then we're going to alternate a 4y1 followed by a 2y2, a 4y3 followed by a 2y4, a 4y to the 5 followed by a 2y to the 6, and so on. And then you're going to end on a 4. So that appears once, 4, 2, 4, 2, 4, 2, ending in a 4, and then that one appears once. So for an n even, okay, we need to have an even number of subintervals. So coming back over to here, we need an even number of subintervals in order to use this theorem, because we need these two endpoints to occur once, and we need the pattern to follow 4 too. So the key to using this is to remembering you need an even number of subintervals. Then the nth approximation is going to be given by this formula: 1/3 delta x times all of those pieces. All right, so let's see this in action. I'm going to jump forward just to show it to you in action. All right, so to have an even number of subintervals, I need an odd number of data points. So 1, 2, 3, 4, 5, 6. You can see there are 9 data points, but our intervals, we're getting 8 intervals or 8 subintervals. So we can use Simpson's rule here because we have an even number of subintervals. So each width was measured at 20-foot intervals. That's my delta x. And remember our formula, just going to show you again, it's 1/3 delta x. And delta x is 20, so it's 1/3 times 20. And then we're starting with the patterning. The first data points occurring once, and then 4, then 2, then 4, then 2, and so on. So when we go through this, this occurs once, then 4 times that one, 2 times that one, 4 times that one, 2 times that one, 4 times that one, 2 times that one, 4 times that one, and then this one occurs once. So again, in order to use this formula, you need an even number of subintervals. And then when you punch all of this into your calculator, you'll get 1,562. Multiplied by 20, you get that. Divide by your 3. That's the approximate area under the curve using Simpson's rule. So that's one option. The other option is to look at Taylor or Maclaurin series. So that's what we're going to do next. So you've already seen a Taylor polynomial. I probably didn't mention that it was a Taylor polynomial. We've seen Taylor polynomials degree 1. We were using them to find linear approximations. We were doing that in Unit 5. So we defined the linearization L at x, which I'm now going to call Taylor polynomial, let's call it subscript 1, or the first Taylor polynomial, to be T1 at x, f at a, f prime at a times x minus a. Now, the first Taylor polynomial, it's called the first order approximation since the following is true. T1 at a is f at a, so plugging in an a and an a, of course that bit will go because a minus a is 0. And if you take the first derivative of this, you'll get t prime at a, that will go, and you'll just be left with f prime at a because the derivative of x minus a is 1. So we can see that this is indeed true. And it is called a first order approximation because you have to agree out to the first derivative. And we determined that it provides a good estimate close to somewhere around a. And in this case, my a was 1. A fairly good estimate close to a. But the further you get away from 1 or a, the worse the estimate becomes. So it turns out you can achieve greater accuracy by using a second degree polynomial. So in this case, we've got C0, a constant, plus a constant times x minus a, plus another constant times x minus a all squared. And the question becomes, what should these constants be? So if it's going to be accurate out to the second degree, then T2 at a needs to be equal to f at a. T, or the second degree Taylor polynomial prime at a, needs to be equal to f prime at a. And the second derivative of that Taylor polynomial needs to be equal to f double prime at a. So if we work through this and we solve them, if we just do an f at a, we're going to plug in our zeros here, and that's going to give me f at a. So C needs to be f at a. So that first little bit is just going to become f at a and solving that equation. And over here, when we do f prime, that piece is going to go. We're going to be left with C1 here. And then we'll get 2 times C subscript 2 times a minus a. But that's going to become 0. And so now I'm going to end up with the equation that says f prime at a must be C1. And when we take the second derivative, this will go, and this will go. And then we're going to get 2 times C2 times the derivative of x, which is 1. So we're going to get 2 times C2 is f double prime at a, which of course means that C2 needs to be 1/2 f double prime at a. So the second order Taylor polynomial is now going to be f at a, f prime at a times x minus a, plus 1/2 f double prime at a times x minus a, all squared. And when we take a look at this, there it is there, that little red curve that I've drawn. Notice how it provides a better estimate over a larger interval. So we can probably extend at least to here and then somewhere over to there. It's giving a better estimate than the line would. Not surprisingly, we can go to a third order Taylor polynomial. And we can repeat all of the math. I'll let you work your way through this. We already knew what these two were. When you come out to the third derivative, you're going to end up with a 3 then times a 2, and 3 times 2 times c subscript 3 should be equal to f prime at, or the third derivative of a, and that should be the same as the Taylor polynomial, the third order Taylor polynomial at a. And if the third order Taylor polynomial becomes this, these two need to be equal to each other, and that's going to give us that c subscript 3 should be 1/3 factorial, the third derivative of a. So now there's our third order or third degree Taylor polynomial is going to look like that. And moving forward, looking at the picture now, that becomes the green one. And you notice how that's going to go a little bit. In fact, that looks fairly good, maybe out to here. So you can see how it's increasing. We can move further away from A and still have a good estimate. So these polynomials are providing the larger the degree, the better the estimate is becoming. So let's take a look at this one here. Now this is the fourth order, or the fourth degree Taylor polynomial. And it turns out that this is 1/2 factorial, 1/1 factorial. This could be 1/0 factorial. 1/0 factorial is 1, 1/1 factorial is 1, 1/2 factorial is 1/2, 1/3 factorial, 1/4 factorial. Then the next one should be 1/5 factorial, the fifth derivative at a times x minus a, all to the power 5. And notice how the purple one is providing an even better estimate. Now let's see if this loads up. And this is just sort of showing you graphically, same thing that I had over there. So the higher the degree of our Taylor polynomial, the better estimate. In fact, it starts to look more closely resemble the curve. So by the time we were the fourth order, we're resembling a much greater part of the curve. More on that later as the lesson progresses. So on an open interval, and we're going to presume that all of these derivatives exist, then we say that two functions, this is a Taylor polynomial, and f at x, agree to order n if the following is true. If we were agreeing out to order 5, then the Taylor fifth polynomial at a would be f at a. The first derivative of the fifth polynomial would be f prime. This would be the fifth Taylor polynomial. The second derivative would be equal to that. Put a 5 there. The third derivatives would be equal. The Taylor fifth polynomial should be equal to the fourth derivative, and then one more. We would take t subscript 5. The fifth derivative of it should be equal to the fifth derivative at a. So if we match, how far out do we match? So if all of these works, the original functions, the first derivatives match, the second derivatives, the third, the fourth, all the way out to the fifth, then we match out to order 5. That's what we're saying. So the Taylor polynomial, subscript n, is approximating f at x all the way out to, just as I've said, order n. So this one would match out to order 5. Now, the Taylor polynomial, so we started looking at this, and now we'll generalize. So the Taylor polynomial, we figured out, in Unit 5, we just actually did these two. I didn't put 1 factorial here. We didn't have the basis for understanding where that came from. So that was the linearization. Then when we come out to a quadratic, it would be this piece, f double prime at a divided by 2 factorial, squared, x minus a all squared. If we want to do a cubic, then the third derivative at a all divided by 3 cubed, or 3 factorial, not 3 cubed, times x minus a to the power 3. Then we would have the fourth derivative at a divided by 4 factorial times x minus a all to the power 4. Stepping out to the fifth, we'd have the fifth derivative at a divided by 5 factorial times x minus a to the power 5, all the way out to, because we want to agree out to order n, you'll be told what Taylor polynomials define, the nth derivative at a divided by n factorial times x minus a all to the power n. And so now I've mentioned already, we saw the first order Taylor polynomial. There's the second order Taylor polynomial. And if we simplify the third order Taylor polynomial, 3 factorial is 6, we will get out to here. And now what I'm going to ask you to do is show, you pick how far out you want to go. This one is going out to order 3. Show that it agrees with f at x to order n. And what does that mean? You're going to have to show that t0 at a is f at a. So not t0, because which one did we say we were going to do? Maybe you're going to do 4. So you're going to show that the fourth Taylor polynomial at a is f at a. The fourth Taylor polynomial prime at a is f prime at a. And I'm just going to write one more of these out, but you'd have to go all the way out to the fourth derivative. So the second derivative of the fourth order Taylor polynomial at a is equal to f double prime at a. And then you'd repeat that for the third derivative, you repeat that for the fourth derivative. They would need to be equal to each other. Once you verified that, then you are in agreement out to that particular order. All right, so this is another way to write that Taylor polynomial as a summation. So the sum from I equals 0 to 1 of, there we had the ith derivative. And notice, in order for this to work, the 0th derivative here is just considered to be f at x. So we've got the ith derivative at a divided by I factorial times x minus a all to the power I. That's a very succinct way of writing all of this out. We can be writing it as a summation. If a is equal to 0, the Taylor polynomial, the nth order Taylor polynomial, is called the nth Maclaurin polynomial. All right, I think maybe we'll start with an example. So find the Taylor polynomial for, I think that should say 4. Let me fix that. For order 4, centered at a equals 3, f prime at x is equal to the square root of x minus 1, and I'm just going to jump over to here. I'm going to copy this for you. I'm going to paste this here, and then I'm going to tell you what it is you're going to need to have to do. All right, the first thing you're going to need to do is get out to, this is order 4, you're going to have to get out to the fourth derivative. You're going to need to write out f at x, f prime at x, f double prime at x, f triple prime at x, the fourth derivative of x. And then you're going to plug in a. A is 3. So we want f at 3, f prime at 3, f double prime at 3, f triple prime at 3, and so on. And then you're going to plug your a in here, and your a is 3. And then you're going to simplify all of that. I think that's enough of a hint, so I guess it's our first time to ponder. All right, resuming and taking this up. So the first thing I'm going to do is I'm going to rewrite this as x plus 1 to the 1/2. The first derivative will be 1/2 times x plus 1 to the negative 1/2. Then for the second derivative, negative 1/2 times 1/4 is negative 1/4. We get x plus 1 to the negative 3/2. For the third derivative, negative 3/2 times 1/4 is 3/8, and we get x plus 1 to the minus 5/2. Again, taking one away each time because these are power functions, or the power rule. Again, the next derivative would be this times that. That's negative 15 over 16. X plus 1, take 1 away from negative 5/2, we get negative 7/2. Now we're going to plug in 3. So if you plug in a 3 here, you get 3 plus 1. Square root of 3 plus 1 is 2. Plugging into here, you're going to get a half times a half. Plugging into the next one, we get negative 1/4 times 4 to the exponent negative 3 over 2. So that's going to be what? An eighth times a quarter. So we're going to get negative 1 over 32. There should be a 3 here. If you can't read that, that's a 3. So again, we're getting 4. The fourth root, or the square root of 4 is 2. 2 to the negative 5 times 3/8 gives me 3 over 256. Again, when we plug the 3 in there, we're going to get a 4, and the square root of 4 is 2. We're going to have 2 to the negative 7 times negative 15 over 16 gives me that numeric value. And then I'm just going to plug right into, I'm going to just paste that over here just so that you can see what I was doing. All right, so pasting right into here. We're going to start with f at 3. F at 3, oh, that should be a 2. Let me fix that. That should be a 2. So f at 3 is 2, f at 3 is 2. And then continuing, plugging in. Now I need f prime at a. F prime at a was 1/4 right here. And 1 factorial is just 1, so I just left that as 1/4. X minus 3 to the power 1. And then we're going to be plugging in, we need f prime at a, or f double prime at a, that's negative 1 over 32. 1 over 2 factorial is 1/2, x minus 3 all squared. Plugging in the third derivative is 3 over 256. 1 over 3 factorial is 1/6, and now the polynomial becomes a cubic. And then the next one would be plus, we need the fourth derivative. The fourth derivative is negative 15 over 2048. We'd have 1 over 4 factorial. 4 factorial is 24, so 1 over 24. And then we've got our quartic here. Simplifying and cleaning up, we get 2 plus 1/4 x times x minus 3 minus, this becomes 1 over 64, x minus 3 all squared, plus 1 over 512 x minus 3 all cubed, minus 5 over 16,384 times x minus 3 to the power 4. So that is the fourth order Taylor polynomial for this particular function. So that says we can represent the square root of x plus 1 by this polynomial function. We are centered at 3 in our example. I'm just going to move this a little bit just so that we can see. That up a little bit. We were centered at 3, so this will provide good estimates close to 3. I'm going to suggest you graph this and this to see how close you can be to 3 before your estimates get pretty bad. All right, moving forward. I'm going to walk you through this Maclaurin example, and then you're going to try one. That's fine. All right, find the Maclaurin polynomial for f at x is equal to e to the x. Remember, the Maclaurin polynomial, it's a Taylor series, but we're looking at our x minus a. For a Maclaurin, a is 0, so we're just going to end up with an x. So first thing we need is f at a, but remember a is 0. So f at 0 would be e to the 0, which of course is going to be 1. And then for the second one, we need our e to the 0, which is 1, plus the derivative is going to be e to the x, but we need that at 0. So that's going to be e to the 0 times x. There's our Taylor naught. There's Taylor 1. And then what we're going to add to that is 1/2. There's the 1/2. For all of our derivatives, I'm just going to write it this way. Fn at 0 is always going to be e to the 0 because the derivative of e to the x is e to the x. So we get 1/2 e to the 0 times x squared, and then plugging into the third order Taylor polynomial, we would now need to add 1/6. The third derivative at 0 is going to be e to the 0 times x cubed. And that's going to give us 1 plus x plus 1/2 x squared plus 1/2 x cubed. Now if we're ready to generalize, the position number, if you like. This is position number 0, and I can view this as x to the 0. There's x to the 1 in position 1, x squared in position 2, x cubed in position 3. That means we need x to the n in position n. And notice where we are here. This is 2 factorial. This is 3 factorial. This is 1 factorial. And this is 0 factorial. So all the way out to the nth term, we would be 1 over n factorial x to the n. That is the general Taylor, or not Taylor, because we're doing Maclaurin, so we could put an m here now. We could replace this with m. The general Maclaurin series for e to the x would be the summation from k equals 0 to infinity of x to the k over k factorial. And if you took calculus, you've probably, for certain if you had me for calculus, we did look at this as an expansion for e to the x. E could be written this way now. E to the power 1, we're going to replace x with 1. We'll get a 1 there. And so 1 over k factorial is a good approximation for e. Moving forward now, you're going to find the Taylor polynomial for ln of x centered at a equals 1. And I'm just going to remind you again, this is what you need. And you're going to need to run through all of the derivatives. In this particular case, I want you to find a general expression for the nth of order n, so the Taylor polynomial order n. First one we did, I said to stop at 4, but this one I want you to extend all the way out to the general case n. And it is our second time to ponder pause. All right, taking this one up and organizing ourselves. So the first thing we're going to need to do is run through the derivatives, all the way out to imagining what the nth derivative would look like. So the derivative of ln x is really 1 over x, which I'm going to write as x to the negative 1, because I want to see this as a power function. So I can then take the derivative of this to become negative 1 x to the negative 2. And for the third derivative, negative 2 times negative 1 is positive 2, x to the negative 3. And the third derivative is going to, or the fourth derivative, is going to be negative 3 times negative 2, which is negative 6, x to the negative 4. So here are the first 4 derivatives. The first thing I would like you to note is the exponent is matching what derivative we're at. So the first derivative, exponent 1, 2, 3, 4. I'm ignoring the negatives. So I hope it makes sense to you why this was x to the negative n. Now, n minus 1 factorial, where is that coming from? So let's see, how did we get this piece here? Where did this piece come from? This was negative 1. Whoops. This was negative 1. This was negative 1 times negative 2. This was negative 1 times negative 2 times negative 3. So I'm going to propose, let's ignore the negatives. Once we ignore the negatives, you can now see this was 1, this was 1 times 2, this was 1 times 2 times 3. So this is a factorial. Fourth derivative is 3 factorial. The third derivative is 2 factorial, and the second derivative is 1 factorial. So the number of factorial we are is 1 less than whatever derivative we're at. So again, the fourth derivative, 3 factorial. So that's why I wrote n minus 1 factorial here. And now I just have to handle that, our negative. When are we negative? So if we are an odd derivative, then we're positive. When we are an even derivative, we are negative. So if I create this expression, negative 1 to the n minus 1, whenever n is even, I'm going to get an odd exponent, and negative 1 to an odd exponent will be negative, which is what I need. And when we plug in our odd exponent, it will return an even one. So this is just changing parity, if you like. If we plug in an original derivative that was even, it'll then make the exponent odd, which will then give us a negative out in front. If we plug in an original derivative that was an odd value, taking 1 away from it will make it even, which will ensure that the coefficient out in front ends up becoming positive. So that's our expression for the nth derivative. And now, where are we centered? We are centered when a is 1, so now I need, these were all at x, now I need the values at a. So I need f at 1, which is 0. F prime at 1 is 1. F double prime at 1 is, or -1, plugging into there. Plugging into here, we get a 2. That should say 1. Plugging a 1 into here, we get a -6. And in general, if we plug in a 1 into this expression, we're going to get a 1 over here. So we get -1 to the n minus 1 times n minus 1 factorial times 1 to the negative n. And if we simplify all of that, let's see what happens. N minus 1 factorial. I'm going to write it this way. And then in the denominator, think of that as n times n minus 1 factorial. That's an alternate way of writing n factorial. So the n minus 1 factorials can reduce, and you're just left with an n. So this little bit here gives us an extra n down here. 1 to any exponent is 1, so that's just going to leave me with -1 to the n minus 1 in the numerator. And then plugging in for our nth order Taylor polynomial, we will start with f at a, which is 0. F prime at a, right there, divided by 1 factorial times x minus a. A is 1. Then we're going to start with our f double prime. There's our value for our f double prime. And I'm now going to need to divide that by 2 factorial, right there. And then we're plugging into the next one, right over here. So I've also done some simplifying as well. Let me pause for a sec just to write some more detail in. All right, so resuming, and I'll give you 2 potential ways to look at it. One way we can look at it is just the second derivative was 2, and then I'd have to plug into, sorry, the third derivative was 2, and I'd be plugging that into, I'd be dividing that by 3 factorial, not 6 factorial. And over here, I'd be plugging in the fourth derivative, which was -6, and I'd be dividing that by 4 factorial. And then we could simplify and see how we're getting those numbers back. Or the alternate thing we could do is just use this expression, which we simplified in general. What do we need to plug in here? We need to plug this in. We need to take the nth derivative at a is 1, divided by n factorial, and we simplified that down to this expression. So what I've done over here is I've actually plugged into this expression here. So -1 to the 1 minus 1 over 1. -1 to the 2 minus 1 over 2, -1 to the 3 minus 3 over 3, -1 to the 4 minus 4 over 4, -1 to the n minus 1 all over n. And again, adjusting for your polynomial pieces. So let's take a look at our final Taylor polynomial. So I want to erase those little extra bits so that we can see. All right, we do not need to write the 0. This just becomes 1 because -1 to the 0 is 1. So we have x minus 1. This simplifies to become a -1. So we have -1/2 x minus 1 all squared. This is going to become positive 1. So that's plus 1/3 x minus 1 all cubed. This becomes -1 times x minus 1 all to the power 4. And now I guess you can see the patterning, because the next one should be plus 1/5 x minus 1 to the power 5, then minus 1/6 x minus 1 all to the power 6, and however far out you needed to go based on what Taylor polynomial you were. So there is the Taylor polynomial for ln of x centered at a equals 1, written down here out to the nth order. All right, let's try one last one. This one is a Maclaurin, and remember, in a Maclaurin, a is 0. You're going to have to look for patterning in this one as well. And remember, I'm just going to paste this over for you here. That is the expression we're going to be plugging into, but we do know that these should all be zeros. All right, another time to ponder pause. Resuming and taking this one up, and for the most part in university, I think you would be given e to the x's, you'll be given lns, and you'll probably be given sines or cos, because they clean up nicely to give us nice Taylor or Maclaurin expansions. So the derivative of sine is cos, the second derivative of sine would be negative sine, and the third derivative would be negative cos. Plugging into the formula, I need f at 0, so sine of 0 is 0. Cos of 0 is 1, negative sine of 0 is 0, negative cos of 0 would be -1, and then this pattern would repeat. So there's the established pattern, 0, 1, 0, -1. It will repeat 0, 1, 0, -1, and so on. So the first thing I'm going to note was that when n was even, so 0, 2, 4, 6, 8, we're going to end up with a sign. It could be either sign, it could be negative sign, but regardless of which it is, sine of 0 is going to be 0. So when n is even, the nth derivative at 0 is going to be 0. If n is odd, then it's going to alternate between 1 and -1. So we're looking at 1, then the third derivative, then the fifth derivative, and that would be the 7th, and that would be the 9th, and this would be the 11th. So we have to ensure that when we are these values, it returns 1. When we are these values, it returns -1. So if we're going to take a look at this little expression over here, 1/2 times n minus 1, which is really 1/2 n minus 1/2. And so when n is odd, I just want to make sure this is returning the proper thing, either 1 or -1. So when n is 1, we're going to plug in a 1, and we'll get 1/2 minus 1/2, which is 0. So the exponent up here is going to be 0, and that's going to evaluate to +1. Let's try plugging in a 5. We'll get 5/2 minus 1/2, 4/2. That becomes 2, which is even. So that's going to return to 1. Plugging in a 9. 9/2 minus 1/2 is 8/2, and 8/2 is 4. We now create an even exponent, so that will come back as +1. Plugging in a 3. 3/2 minus 1/2 is 2/2, which is 1. The exponent's odd, that comes back as -1. 7/2 minus 3/2 is 6/2. 6 divided by 2, of course, is 3. The exponent's odd, we get a negative. Just do one more. 11/2 minus 1/2, 10/2, which is 5. The exponent is now become odd, so that will return -1. So this is definitely working. This is returning 1 when we need it to, and it's returning -1 when we need it to. The problem, however, with this is when I head out to generalize, I'll explain that little bit. Why does that bit need to be there? But let's work our way through it. So we're now going to have 0, and then we're going to have 1 over 1 factorial times x minus 0, plus 0 over 2 factorial, x minus 0 all squared. Then we have minus 1 over 3 factorial, x minus 0 all cubed. Then we have 0 over 4 factorial, x minus 0 all to the power 4. Back to the 1 again, plus 1 over 5 factorial, x minus 0 all to the power 5. Plus 0 over 6 factorial, x minus 0 to the power 7. And the next one would be minus 1 over 7 factorial, x minus 0 all to the power 7. Now coming out here, we've established that this little bit, we can see in each one of these, there are the factorials we need, right? So definitely n factorial. I've established that this will return 1 and -1 based on n correctly. I'm just going to now have to handle, because this is going to return a value when we're at our even bits here, right? I need 0 to come back, and 0 isn't going to come back from here. This is going to return a number other than 0 when we're hitting our even derivative. So I'm going to correct that by this little bit over there. I am going to show you x to the n. Again, there's a match right there. Position 0, position 1, position 2, position 3, 4, 5, and so on. So there's a dead match there. So this should be x to the n. Now I've created this little bit over here. I need this bit to be 0 when n is even, and I need it to be 1 when n is odd. So how did I handle that? So if we look in position 1, when you plug in the first position here, like that's the 0th derivative, right? So a 0 is coming there. That's the first derivative. So when we plug a 0 in here, 0 plus 1 is 1, and -1 to the 1 will be -1. And 1 minus 1 is 0. So that cancels out. When we plug in for this little bit here, just to show you that this is working, that becomes 1 plus 1. It's even now, so this is positive. 1 plus 1 is 1, or 1 plus 1 is 2, and 2 divided by 2 is 1. So I'm getting a coefficient of 1. That's fine. When we move to this one, which is the third position, Yeah, it is the third position in. However, this is the second derivative, so it's an even derivative. So I'm going to plug a 2 in here. 2 plus 1 is 3. The exponent is negative. This becomes negative. 1 minus 1, 0. That drops out. And we're going to get our 0 back. Moving into this one. This is the position of the third derivative. So we plug in a 3. 3 plus 1. Even. So this becomes 1 plus 1 over 2, which is just 1. We'll do one more. So that's the position of the fourth derivative. We plug in a 4. 4 plus 1 is 5. Odd number. That means this is going to be negative 1. 1 minus 1 is 0. So by adding this little bit here, this bit is 0 whenever you're an eventh derivative, and this bit becomes positive 1 whenever you're an odd derivative. And then that allows me to come up with a general term for n. And remember, this was a complicated general term because we had to account for the switching from 1 to negative 1, and we also had to account for the fact that every other one of these would be 0. All right, so that has done it for us. So simplifying, what happens? The 0 goes, we're getting an x here. The 0, that's gone. We are minus x cubed over 3 factorial, that goes. Plus x to the 5th over 5 factorial. Minus x to the 7th over 7 factorial, and then we would be plus x to the 9th over 9 factorial, minus x to the 11th over 11 factorial, and so on. Now, if we want to clean this up to make the general term a bit prettier, because it's this little bit here, let's just allow n to be 2u plus 1. So now I'll call this the Taylor term for 2u plus 1. So it's the order 2u plus 1. None of this will change. This little bit here, how will this change? So I'm going to replace the n with 2u plus 1 minus 1. I'm going to replace this n with 2u plus 1. I'll replace that n with 2u plus 1. And I will replace this n with 2u plus 1. And then what will happen over here? None of these are going to change, but over here, 2u plus 1 minus 1 is just 2u. 2u divided by 2 is u. So this just becomes a u. This stays the same, 2u plus 1 factorial. This isn't going to change. It's 2u plus 1. But what happens over here now is 2u plus 1 becomes 2u plus 2. And 2u plus 2 is always going to be even. If this is always even, then we're going to get 1 plus 1, which is 2, over 2, which is 1. So now I don't need to write this piece because it's just going to be 1. So in general, the Maclaurin polynomial for sine x could be written as this: x minus x cubed over 3 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and out to order n, negative 1 to the power u divided by 2u plus 1 factorial, x to the 2u plus 1. All right, now why would this be useful? And again, I get that this is a lot of work. Hopefully in a university exam you're not asked to do too many of these or go out to an order that is too high, because it is a lot of work. You've got to find all the derivatives, you've got to plug in your a value, find the numeric value for that, plug that into the general formula for the Taylor polynomial, and simplify. So yes, these were a lot of work. Is it easy to make a mistake somewhere along the line? It most certainly is. Again, the ones we were looking at, this one doesn't clean up as nicely, again, because this wasn't an e to the x or a ln of x. The formula for e to the x is very pretty, and the formula for e is very pretty. The formula we're getting for ln of x is very nice because it's simple to extend that pattern. It's not so simple to extend this pattern. Can you tell what would be the piece that would come next? You could certainly tell what degree it would have, but could you tell what number it would be based on the patterning you're seeing there? Much simpler to do it here, and very simple to keep extending this one. Now, why would we use this? So let's take a look. Sine to the x over x does not have an explicit indefinite integral. So that means you can't come up with a basic function to represent it as an antiderivative. But what we can do for these ones that don't have explicit indefinite integral formulas, we could write them as a definite integral, or we could write it as an infinite series. So the Maclaurin expansions of sine we just saw was this. Therefore, sine x over x, we could just take this and divide this by x. So if I divide by x, I get a 1. I get minus x squared over 3 factorial, plus x to the 4th over 5 factorial, minus x to the 6th over 7 factorial, dividing each of these by x. So then if we wanted to integrate, and we would have to extend that pattern. If we wanted to integrate sine of x over x, then we would be taking the integral of this particular function here. 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial, and so on. Now going backwards on 1, we would get x. Going backwards on x squared, it would be x cubed over 3, and we need the 3 factorial. Backwards on x to the 4th is x to the 5th over 5 factorial. Backwards on x to the 6th, that's x to the 7th over 7 factorial. And then we would be going backwards on x to the 8th, and that would be x to the 9 over 9, and then your 9 factorial. So if we generalize, we can see here that this position is 2n minus 1. So we have 2n minus 1 factorial times 2n, and you can simply test this out. This is the second position in. And 2 times 2 minus 1 is 3. The third position in. 2 times 3 minus 1 is 5. 2 times 4 minus 1 is 7. So those are matching. These exponents up here, if we're trying to figure out what these ones should be, they're all matching. All of these numbers are the same. So this would be 2 to the n minus 1. And then the only thing you have to worry about now is the alternation of signs, right? So the first position versus the second, and so on. So in this first position here, in this first term, when I plug in a 1, 1 minus 1 is 0, and negative 1 to the 0 is positive. When you go to the second position, you get 2 minus 1, that's 1. Now you return the negative 1 you need. In the third position, 3 minus 1 is 2, returning the positive. In the fourth position, 4 minus 1 is 3, returning the negative you need, and so on. So in general, this summation formula, we could now replace this antiderivative, if you like. We could write it as a summation. It's the sum from n equals 1 to infinity of this particular formula. Now, to give it a numeric value, obviously we're going to have to punch in and do some number crunching. All right, I thought I would end this by showing you in Desmos. So I'm going to slide this over a little bit just so that I can see my controls. All right, that is the graph of sine x over x. And then I've got the Maclaurin polynomial here. And on the Maclaurin polynomial, I went all the way out to 1, 2, 3, 4, 5, 6, 7. So I guess we've got 7, really 14 terms here if you're going to count the ones that were 0 and they've dropped out. So I've got 7 terms here. Now, this is centered way over here at 0, and look how accurate it is. I mean, we can be correct for our predictions between maybe 5 out here to negative 5. So I'm confident my prediction from very close to negative 5 all the way out to positive 5. What I'm going to do now is I'm going to show you. So here is our Maclaurin polynomial taken from over here. There's our Maclaurin polynomial for this, or our Maclaurin expansion. That's what I used for here. And so there's 1, there's 2, 3. And see, every time we add, how much better that's getting at approximating. And then it sort of just continues. I'm going to have to pull this back over a bit so I can get the zoom. It's going to shrink that a bit. I just wanted access to the zooming, so that you can see as I add more, it just gets better and better and better and better and better. So now, even though that this polynomial is centered at 0, we are making accurate predictions from negative 30 all the way out to positive 30. And you see that your calculator is probably using a Maclaurin series to evaluate. When you punch in sine of a number, it's likely that it's using a Maclaurin series. All right, so let's back this down. Whoops, see if it will let me back that down a bit. I'm going to hide that. I'm going to hide that. And then I'm just going to come down to let you take a look at this. So I wanted the integral from 0 to 4 of sine x over x. I've evaluated that in Desmos. In this particular case, I'm just using a Maclaurin polynomial, and I'm going to stop my evaluation when I get out to this particular bit, 1, 2, 3, 4, 5, still the 7 terms we had before. And this one I'm going to call P at X, and I'm going to just change N up here to see how much better our estimate gets. So our estimate for M at 4 is never going to change. It's always going to stay here because I only have the 7 terms here. Initially, the estimate for P is not so good, but notice how when we add more terms. All right, so here we've got the exact same number of terms there. And now how much further do we have to go before our estimate matches? Right there. So we only had to do 13 terms in this polynomial to be accurate to 1, 2, 3, 4, 10 decimal places it looks like. So I only needed 13. I only need to do that 13 times. Now over here we are getting more accurate, but the decimal places are so far over we can't see them in here because this is only how many decimal places Desmos will let me see. So I hope what you're getting out of this is Maclaurin and Taylor series are very useful. Let's come back to these graphs now. For evaluating or trying to find an indefinite integral or a formula for an indefinite integral for something that doesn't have one. So for example, sine x over x. It doesn't have an explicit formula, but we were now able to use this Maclaurin expansion to come up with an answer. So that's what this lesson was about, either using a numerical integration using Simpson's rule or taking or making use of a Taylor polynomial or a Maclaurin polynomial to come up with an infinite series. So this is really an infinite series, and that will give you the best estimate. All right, once again, I think this was a bit longer of a lesson because it was more on the complicated side. So if you were able to make it to the end, good for you. Once again, thank you for supporting and watching. Don't forget to like and subscribe. And as always, take care and be safe.